good evening. Take my greetings according to your timing. So it's me, Ayushi Sarkar, going to teach you stereochemistry for your engineering classes. So, I will just give a short recap of the stereochemistry introduction, as I have already taught this in my previous lecture. You can refer to it. So, meanwhile, I will just give you the whole brief and will continue from where I have left. So, the stereochemistry, the branch of chemistry which deals with the 3D structure and molecules and their basic physical and chemical properties, is known as stereochemistry. The significance of stereochemistry is written over here. So, firstly, a thalidomide, a disaster. Why it is called as disaster? Because in a pharmaceutical company in 1957 in Germany helps to treat this is anxiety, trouble in sleeping, morning sickness in pregnant women. So this thalidomide, this drug is actually a sedative medicine. You know what is sedative? Sedative is something which helps, it's like it helps you to remove your anxiety, stress and everything. These are known as basic sedatives. But the thing is what, due to the use of this thalidomide in pregnant women, what has happened, we can see actually there is two types of thalidomide present. I will read it out for you. Severe genetic damage of early embryonic growth and development has occurred. Limbs deformation, limbs deformation has occurred, and many things. Almost 10,000 babies with severe deformities, thousands of miscarriages has happened. So why this has happened? Because this thalidomide is a racemic mixture. And what is racemic mixture? Actually, where the A strain and R strain, both of the strain is present in it. That means this thalidomide is of two structures. This is the S structure and this is the R structure. You know what? This thalidomide S is a tetragenic nature. So what is tetragenic in nature? Cause defects and in embryos and fetus. But this R was the effective one. So what do we need? We need the R strain, right? But what has happened, due to this racemic mixture, we had both S and R together in the same compound, due to which this kind of disaster has happened in Germany. So finally we get to know what is this. So tetragenic means it is having mercury, lead or retinol type of things. Alright. So coming to the molecules with similar formula can be classified as homomers and isomers. Okay, I'm going for the classification. So please concentrate over here. This is very important for your examination, for an overview of the whole chapter, what we are going to study later. So isomers, homomers and isomer. So homomers are basically identical in nature. Okay, so the similar molecular formula are identical in nature, are basically the homomers. And here constitutional isomer and stereoisomer. What is constitutional isomer and stereoisomer? We are going to read here the stereoisomer in the whole chapter. But what is constitutional isomer? I hope you all know. This is a structural isomer. What is structural isomer? Here you can see there is one fluorine present in both the structures, but the number of carbon in which it is present is not the same. Here it is one fluoro, but here it is two fluoro. So this is the fine difference. Fine. So once we get to get deeper into the stereoisomerism, we can see that what is stereoisomer. It is a spatial type of arrangement, not the constitutional one. It's a spatial arrangement. What has happened to it? Let's see. There is two types of stereoisomer, which is diastereomer and enantiomer. I will discuss it later, that what is diastereomer and enantiomer. Let me give you a basic for the classification of it. Okay, so the mirror image is called as enantiomer. Fine, non-superimposable mirror image. But diastereomer is not the mirror image. Diastereomer can be further classified as cis-trans isomers or conformers. Yeah, we are going to read each and everything, but you need to wait for the whole lecture. One by one I will upload the lecture, you have to follow it. Fine. sun trans isomers and conformers. So after this we get to know what is the definition of isomer. Iso means same or equal and mers means parts. Okay, different compounds having the same molecular formula are called as isomers, and this phenomena is known as isomerism. Fine, I hope it is clear, the description is quite clear. And while coming to the stereoisomerism, I will just read the isomers having the same constitution but different spatial arrangements of their atoms are known as stereoisomerism. The isomerism exhibited by them is called as stereoisomerism. Okay. Then enantiomers, isomers which are non-superimposable mirror image of each other are called as enantiomers. Optical antipodes or enantiomorphs, okay, or mirror image isomers. Okay, these are four synonyms. And coming to the next, that is our diastereomerism. What is diastereomerism? The stereomerism which are not the mirror image with each other exhibiting the diastereomerism. That means they are not the mirror image. This is the main classical point. Fine. So let me contribute to the types of stereoisomerism on some basic things. First is optical isomerism. Another one is geometrical isomerism. Fine. If I will come to the topic of optical isomerism, which is our today's special topic, I will complete this optical isomerism by today so that you can get to know about more in our next classes. Fine. So optical isomerism, what is optical activity? First, knowing before what is optical isomerism, you need to know what is optical activity. Compounds which rotates the plane polarized light are called as optical active compound. Okay, that can, you have studied this experiment in your +2. Okay, that a plane polarized light will be passed through compound. Okay, and if this compound can rotate it, this is called as optically active compound. Fine. So this is what the thing is. Okay, so this is the optically active compound. Now coming to the division. Optically active, that means one which can clockwise rotate the light is known as dextrorotatory form, and another one which can rotate the light in anti-clock direction are known as levorotatory or minus form. Okay, and once we complete this, we would know what is polarimeter. So what is polarimeter? The instrument used to detect optical rotation is called as polarimeter. The degree of rotation depends on the following factors. These are the following factors on which this rotation, the degree of rotation will depend. So what are this? First is the nature of compound. Fine. The nature of compound actually depends on how is the solvent is. So these are the next points. The second is our temperature. So first is nature of compound, second is our temperature, third is our solvent, concentration of the solution, also lambda of the light, that means wavelength of the light. Fine. These are the following factors on which the degree of rotation, and this degree of rotation can be noted as our alpha. Okay, will depend on. So fine, I'll move to the next topic, that is our alpha, specific rotation. Sorry. When I'm telling about the specific rotation, it means that the measurement of optical activity which is reported in the terms of specific rotation. Fine. What is this alpha? Alpha is our specific rotation. Okay, so alpha limit from lambda to t. Okay, that is t is for standing for the temperature and lambda is standing for the wavelength. Okay, and alpha is our angle of rotation and length is the sample of the tube. Okay, in decimeter, and c is for concentration of the sample. These are the factors which is used, and this is the formula. I am just enriching the formula with the square so that you can understand, and you don't need to muggle up this formula. It's of no use. I have given you to define what is specific rotation for your purpose. According to the engineering chemistry and my past observations, I have clearly seen that in stereochemistry no one is going to ask you the definition or no one is going to ask you the formulas. The things which they are going to ask you is very basic and simple. They want to know that you know the difference between different type of isomerisms or not, means like stereoisomerisms or not, the configurations, and this is the points and examples. These are the questions where you will be stand. Okay, so finally I could say you one thing very clearly, that you don't need to take tension about the definitions. Okay, so you can just, I have written this all the stuff for your purpose of understanding, so that when you will just revise before the exam, it's not possible to complete all the lectures before one day. So you need to do what? You need to go through your notes, and once you go through your notes, everything you can visualize in front of your eyes. So that's why I have written all the formulas, all the descriptions over here. You don't need to muggle up, and what you need to muggle up, I will write it over here. You just need to remember those points as well. Fine. So what is optical isomerism? Let me give you a definition. Fine. What is the optical isomerism? It is said that compounds having same molecular formula but differ in their behavior towards plane polarized light. This is plane polarized light. Okay. Due to different arrangements of atom molecules in the space are known as optical isomers, and this phenomena is called as optical isomerism. Okay. So what are the common properties? So they have same physical and chemical properties. Okay. The optical isomers will have same physical and chemical properties, and the number of optical isomers present is given as 2 to the power n. And what is this n? N is the number of chiral carbon present in the compound. I hope you understand what is chiral carbon. If not, I am just showing it over here. This is the chiral carbon who have different groups in its 4 arms. Okay, this is group A, this is group B, this is group C, group D. Okay, there will be asymmetricity in the whole carbon. A single chiral carbon means it will have one optical isomer. Fine, this is the whole description and all. So let me introduce you with the terms that is important for this optical isomerism chapter. Okay, first term is already been described a bit, that is our enantiomer. I hope you remember the term enantiomer. Okay, let me take another pen. Okay, enantiomer. I will write a short description for just revision purpose and will give you the example. That is the main thing. That is my main motto of doing this class, because I am going to discuss and giving an end to this optical isomerism topic today. Okay, enantiomer. What I have already discussed in this lecture. What is enantiomer? Enantiomer is, I would request each and everyone who is seeing this lecture to just open their notes and complete it with me, so that you don't need much time after completing the lecture to complete your syllabus. You can do it with me as well. What I usually say in my live classes, the same thing I am going to repeat over here as well. So what is enantiomer? Firstly, optical isomerism. Write it with me. Optical isomerism with non-superimposable mirror image. I hope you remember. Superimposable I request to just neglect my any kind of spelling mistake. Sorry. Okay, fine. So I will give some examples of you this 2 to the power n thing. So first example, I will take a very common one where 2 to the power n value is our 1. That means it will have only 2 to the power 1, that is our 2 forms. First, let's see. So first form is, the first example is, these are 2 examples I am going to take. Okay, so first is our lactic acid. Okay, lactic acid. This is important, so I'm writing it in a bright color so that you can recognize that this is important. Lactic acid, fine. So lactic acid is having okay, wait just a second. I am giving you the whole description from here. Sorry, my bad. Lactic acid. So what is the formula of lactic acid? It's basically, let me write it over here. C3 CH3 OH COOH. Okay, this is the formula of lactic acid. So let me brief it with the form. You can see the chiral carbon. Let me draw this for you. Okay, I am taking this. This is our chiral carbon. Okay, how I am showing it to you. See, in one hand I am having hydrogen. Fine. In another hand I will have OH. Fine. And in another place I will have CH3. Okay, and another this acid group COOH. This is the complete thing. Okay, so you can see this is our chiral carbon. Another form which can happen, that is our just interchange of this O and H. How? CH3 as it is, COOH as it is. Fine, but it would be mirror image. So it is OH here and H over here. Fine, let me draw the mirror within. I'm sorry. Fine, let me draw this mirror. Okay. So this is our chiral carbon, as you can see. The C is our chiral carbon. And how it is going to rotate? So you can see here, this is one chiral carbon present. So 2 isomeric form. That means 2 to the power n is having n is equals to 1. That means 2 to the power 1 is our 2. These are the two forms that you will get. Okay, so finally moving to the section how you will rotate dextrorotatory and levorotatory, which I have already made you understand over here. Let me come to the page. Okay, here see, if you rotate in a clockwise direction, that means it is a dextrorotatory form, and if you do it in an anti-clockwise form, then it is a levorotatory form. And how are you going to see this rotation? So first, seeing the rotation, you need to identify first that which is the prior group. See here, obviously you have to move from the least prior to the most prior one. How will you do this? Here you can see H, hydrogen, is the least prior ones, and you can see here this is our most prior ones. Okay, how will you move from here? You will go through this direction. Okay, and it is coming to be, see, you will go from this direction, and this is our clockwise direction. Fine. So this is called as what? Dextrorotatory. This is our D form. I am writing it for you. It's our D form. Okay. And here you can see this is our hydrogen, and this is our alcoholic group. So how will you move from this to this? So this time you will go from this anti-clockwise direction. Okay, this anti-clockwise direction. And this is, see, I am going to teach you how will you see this configurations and all in our RS configuration topics. So please wait for that. I'm just telling you and giving you the examples of this optically active compounds and also just go for this, and then I will let you know how to see the configurations and everything. Okay, this is our L form, levorotatory form. Fine, and because this is in anti-clockwise direction. This is our lactic acid. Done. So our next example is going to be where 2 to the power n is equals to what? 2. So next topic is our wait just a second. Yes, next topic is our 2 to the power n, that is our tartaric acid. Okay. But before that, what is tartaric acid? Before I move to it, as you can see that tartaric acid is not superimposable mirror image. So we have another form of optically active compound, that is our diastereomer. Okay, I will just take an example of it and will make you write it. Okay, diastereomer. Fine, diastereomer. Diastereomer can be written like this way. Optical isomerism or optical isomer. That are not mirror image. Simple. Of each other. Okay, so let me contribute over here. I'm going to make you understand what is tartaric acid. So let's take an example of tartaric acid. Fine. Tartaric acid. I hope you are making notes with me. Okay, fine. So this tartaric acid, how will you figure it out? So it is having a formula as C2H2OH whole 2 and COOH whole 2. Okay, this is the formula. And how are we going to make it? Okay, let me show you, draw one thing for you. This is our chiral carbon. Let's see this chiral. I'm taking this carbon. Okay, I'm having one hydrogen. Fine, I'm drawing it over here, hydrogen. And again I'm having a alcoholic group. I'm writing this alcoholic group from here, OH. Fine. And you know you have to add acidic group as well. You have two acidic group, one acidic group. I will give it over here. Another one, what I can do, I then rest of the thing I will write in the same form. I will just repeat this form, this whole thing, this form. Just I will just copy paste this whole thing. Okay, copy, just same thing. You don't need to do anything else. Best. Okay, fine. See, I am just writing it and would remove it as well. Second, fine. Okay, this is one form, and I'm adding this OH over here, COOH, and this will turn to be our opposite sides. So this is turned to be our OH and this is our H. So this is one form. Here you can see what I'm taking another color for this. This is one chiral carbon, because what are we having? This is a acidic group, this is a hydrogen present, this is another alcoholic group, and this is completely another group. And same wise, this is also a chiral carbon. I'm taking another color to denote this chiral carbon. This is also chiral carbon. How? The same way. This is our hydrogen, this is our alcoholic group, this is COOH, and this whole group, okay, this is also a different group completely. So you can see, okay, this is our tartaric acid complete formula. So what can you see from here, or what can you deduce from here? You can deduce that 2 to the power n is equals to, here n is equals to 2. That means you are going to get 2 to the power 2. That means 4 formulas. So how you will make this 4 formulas? Okay, just I will do nothing. This time I am going to use a simple thing. Copy, paste. Fine. This is the thing. Okay, what you need to change, I will show it to you. I request every one of you to draw this kind of formulas again and again in your notebook, so that in exam you can draw it effortlessly. You know what, the thing which are going to come is this only, the tartaric acid formulas, and it is optically active or not. This kind of question is definitely going to come, so that you can get a form of idea that how you can use it. Okay, this is the thing. So let me show you which is optically active and which is optically not active. These are the 4 forms you are going to get. Okay, see here what I am going to change. I'm going to change what? This is our OH, this is our H. This was the first formula. Then I will do what? Next, I will going to be interchanging the positions of H and OH. Okay. So here I am going to write H. Here I am going to write OH. This is our OH and this is our H. See one thing over here. Here I hope you can see that this is basically, I'm taking the mirror. This is the mirror image of each other. Okay, so this is the mirror image of each other. So these two are enantiomers as well. This 1 and 2. This 1 and 2 is enantiomer to each other as well. Okay, fine. And here what I am going to change, see. Let's say this is OH. I am writing OH over here and H over here. Okay, so you can see here the chiral carbons are same, but the thing is what, this OH are on the same side and hydrogen is on the same side. So they are basically what, they are over here, and here you can see they don't have that enantiomeric property with respect to 1 and 2. They are completely different. So this 3, this is third and this is our fourth. This third and fourth are distereomer with, okay, let me draw the 4 as well for you. So this time this is hydrogen. I'm going to keep this hydrogen over here. I'm going to change it from here. Okay, let's see. This is our hydrogen and this is our OH. Okay, so you can see this is completely different from each other. So this 3 and 4 is distereomer with respect to 1 and 2, but they are enantiomers with respect to each other. How? Okay, let me draw this for you. If something has happened or not, I couldn't see. Okay, fine. I'm drawing this for you. Okay. I'm writing it. These are the 4 forms, but you can see that 1, 2, 3, 4, they are distereomer to each other. Means like 1 and 2, I'm writing here, 1 and 2 is distereomeric with respect to 3 and 4. To 3 and 4, but enantiomer form one and 2. Okay, and 3 and 4. Fine. These are enantiomers and diastereomers. They all are diastereomers to each other. So which are optically active and which are not optically active? I will go for this discussion. Fine. As you can see, the optical activity depends on the chirality of the carbon. So see, I am showing you how you can see this is optically active or not. Let me take another magical pen over here. Okay. What's wrong? I don't know. Sorry. Is anything wrong? Okay, sorry. Okay. See, here, this is I'm drawing over here. See, this is something you can see. I'm drawing a line. This is half. So from here you can see that you will move from lowest to the highest. How will you move this? You will go from this direction. Fine. You are doing what? You are going anti-clockwise. Okay. And again you will go from here to here. This is our not in the form. Sorry, there is something wrong with my explanation. Just wait a second. Let me revise my explanation so that you can understand it in an easy way. Okay, just a second. Okay, see how you can say that this is optically active and this is not optically inactive. So here when you will just divide this, you will go from this position, from hydrogen to oxygen. You are going like this way. Okay, you have seen that you will have to choose the lowest priority order to move from one direction to another. So hydrogen to oxygen, you will go like this way, and again later from here you will do the same thing for this. Okay, so finally you see what they are opposite to each other. Okay, and they are optically active form. But when you are going for this is hydroxy and this is hydroxy group, and same way you will go from here to here like this way, or you will go from here to here in the same direction. So basically they will cancel each other out. So this is the optically active one, this is active one, this is also active one, this is inactive one, this is inactive one. Okay, and I'm really sorry if you have found any error in my writing and all. So I hope you understand the whole thing. So let me come to the next part. Some examples I will give you and will bind up this lecture because it's going to take much time else. So next is our some topics, means some examples that doesn't depends on the optically active compound but without chiral or asymmetric carbon atom. I'm giving you such kind of example. Okay, so make a heading for it another way, that optically active compound without chiral or asymmetric carbon atom. Okay, okay, come over here. So my first example is going to be, see, these examples are very important, so I request you to learn all the examples, please. So first is our biphenyl ones. Biphenyl. Biphenyl derivatives. Okay. So what is biphenyl derivative? Let me draw it for you. Whenever you see biphenyl, I'm just decoding it. I hope in plus 2 you have already learned all this stuff. But still, why am I showing you all this thing? Because once you revise the things, you get to know about it more and give a clarity so that you can effortlessly draw this in your upcoming exam. When you are seeing biphenyl, phenyl group is our benzene. Fine. I'm going to draw benzene over here. Okay, and bi means 2, where 2 benzene will get connected to each other and basically known as biphenyl derivatives. So let me draw beautiful benzenes for you. Okay, this is our biphenyl group. Okay, this is our biphenyl group, and here I am going to attach derivative, means this is a sulfonic acid, let's say. Okay, I'm adding sulfonic group over here, SO3H. This is a sulfonic group. Okay, then what will I do? I will just copy paste this and will change the positions, nothing more. Copy, paste it over here, and will change the positions. See, they are mirror image to each other. I am saying this before, earlier only, they are mirror image to each other, but I should. So this sulfonic group will change, and how will it this change? See, SO3H. Here this is the sulfonic group. If it would have a mirror image, where it would be, it would just convert it over here. This is our enantiomer and SO3H. Fine, this is our mirror image. And then you can see SO3H over here, then it would be over here, SO3H. Fine, done. This is mirror image. I'm showing this mirror so that you can distinguish which is diastereomer and which is enantiomer as well. I'm drawing the mirror for you. Okay, so they are known as biphenyl 2,2-disulfonic acid. Okay, this is non-superimposable mirror image as well. What is the name? This is going to be our biphenyl, sorry, bad, biphenyl 2,2-disulfonic acid. They are enantiomers. Enantiomers. Okay, I hope you understand this. Next, I will go for the next example, that is our allenes, and we have only 2 more examples left for today's chapter to complete with this optical form and all. So I'm just making sure that I can write and complete it over here. Okay, fine. This is our biphenyl derivative form. Let me take this over here. Just give me a bit of seconds so that I can correct everything and make you write the next thing. Meanwhile, I will request you to just pause the video and complete the notes along with me. Okay, so I will put it over here. Sorry, just a second. Okay, fine. Okay. This is just a second. Optically active compound without chiral asymmetricity. Fine, this is our another example. Let's go move for the next example. Sorry for the time. Next example is going to be our spiro compounds. Okay, these are, I know this is a bit difficult to recognize and memorize, but still I suggest you to at least recognize a single structure so that you can write it over there. This is the spiro compound, or aka known as spirines. Yes. Okay, what is this? Let me go for it. So this structure that is actually in a form like it's completing a whole loop. It will not have any chiral carbon, but it will form a different type of loop. Let me show you some amino compound. Okay, basically amino group is the thing that usually create this type of thing. I am drawing the carbon and it is having hydrogen amino group. This is our CH2. So CH2. Okay, this is our carbon again. So CH2. This is our CH2. This is our carbon. Sorry. This is our H. This is our NH2. The amino group. So what is the name of this compound? This is basically 2,6-diamino spirocycloheptane. Why? I hope you understand why I don't go for the nomenclatures and anything else over here, because we are studying stereochemistry here. So this is the name is what? This is our 2,6. From anywhere you can start naming it. Okay. Diamino pyro cycloheptene. Okay. So our last and final compound is going to be allenes. Let's go for the allenes. You know who are allenes? Where you have this double bond on next to each other. That means I am showing you it. When this group is present, this C double bond with this group is present, this is our allynic group. Okay, so I'm giving you the basic example, that is our diphenyl propadiene allene. Okay, so how will you draw this? Firstly, allene group, obviously this is allene present, so allene group, this is the allene group, and next to it I will just add carbons. Okay, here what I will do, hydrogen, I'm going to get here C6H5. There is our phenyl, diphenyl, I have already told you the name. So from there you can see this is our diphenylic group. So again another phenylic group over here, CXH5. Okay, fine. And this is our, okay, here you will see that who is, this is our fishtail projection. You can see this is our H, this is in the downwards, and here you can, as you can see here, okay, sorry, this is the form. I'm just going to do what I'm going to create a mirror image of it. Okay, copy, paste. Fine. Instead I will have a proper drawing of this. This is mirror image, and let me draw the mirror image of it. I don't know why I used to do this copy paste when I know that I have to create this mirror image. Okay, this is our form, and here if you start creating the mirror image, here you can find hydrogen, fine, here you can find C6H5. Okay, and this C6H5 will go over here, C6H5, fine, and here you can see the projection of H. I'm saying this, what is this? They are mirror image to each other. What is the name of it? Let me name it first, then I will go for it. This is our 1,3 diphenyl propadiene. Okay, so this is also a mirror image. I want to draw the mirror for you. Wait just a second. Okay, fine. This is our so-called mirror. So I will bind my lecture over here only, because I have already completed the optical part. From next day I will be starting with RS configuration and all. So as far I have taught you, I hope you will complete your notes, and if any doubt have regarding all this thing, you can just let me know. And one more thing I want to add, that what is the condition for a compound to be optically active, that I think I have written it or not. I just, let me check it once. No, I have not. So let me add it over here as well. Just give me a second. I will just add it with this lecture, else it will remain to get completed. Okay, just a second. Just give me a moment. Let me finish it. Let me finish it. Okay. Oh no, shit. I have. Okay, leave it over here. I'm just adding a new frame and writing why do we need and what are the conditions for optically active compound. Okay. Conditions for optically active compound. First is our at least one chiral carbon, that is very normal. Or asymmetric carbon. Okay. Second is our have plane of should not have a plane of symmetry. Should not have center of symmetry as well. Okay, these are the 3 points that are the conditions required to be a optically active compound. Fine, I hope so. Let's meet on the next lecture someday. So before that, I request each and every one of you to complete the whole notes and send it to me. So if you have any doubt, you can ask in the comment box or you can just DM me over there. So thank you. Let's meet on the next lecture. Bye bye.